Okay, thank you very much again for inviting me here to give a talk. So I will be talking not only about vitrimers, but about polyhydroxyurethanes, their modification, and as a result of this modification, a route to create polyhydroxyurethane vitrimers with dioxaborolane dynamic bonds. So I would like to give a short introduction about polyurethanes in general. So it's a class of polymers composed of two different monomers that are considered a commodity plastic because they're produced on really large scale and used in multiple applications, which you can see on the slide. And that defines that the market for polyurethanes is constantly growing, constantly developing, and most of polyurethanes are thermosets and are used as foams. I think around more than 60% of all produced polyurethanes, but still there are a lot of thermoplastic polyurethanes. Mostly it's so-called TPU, thermoplastic polyurethanes, and they are elastomers or hard thermoplastic polyurethanes, and they also use for example, in footwear and automotive industry. So polyurethanes are readily synthesized by reaction of isocyanates and polyols. And depending on the composition of the functional groups, if it's difunctional monomers or polyfunctional monomers, we will have linear polymers or thermosets. However, isocyanates have one huge drawback: they're toxic. And more to that, so they are synthesized from really toxic starting compounds, aromatic diamines or polyamines and phosgene, and these aromatic amines are coming from fossil resources. One more disadvantage of polyurethanes is that they have poor recyclability. At the end of life, they are just disposed and it's hard to recycle them. Alternatively, quite long ago, an alternative route was suggested to use the reaction between cyclic carbonates and diamines, which mostly are aliphatic because they have high reactivity towards ring opening of cyclic carbonates. And so that's why they are less toxic than aromatic ones. To have a similar class of polymers which mimic the polyurethane structure, but have a little bit different structure because they have pendant OH groups in the polymer backbone. So starting compounds for this class of polymer called polyhydroxyurethanes, which are considered one of the potential alternative to polyurethanes, also can be sourced from bioresources. That's another advantage. However, currently, this class of polymer has several issues. First, the kinetic of this aminolysis of cyclic carbonates is quite slow. That results in low molecular weights of polyhydroxyurethanes. Moreover, there are some side reactions that are going on concurrently with the main ring opening that also limits the molecular weight. Moreover, as I already indicated, that we have pendant OH groups in polymer backbone, and that gives us high hydrophilicity of the polymer. This high hydrophilicity results in significant moisture uptake in humid environment or upon storage, and subsequent deterioration of mechanical properties of the polymer due to plasticization with water. And due to these problems and issues, there is currently no practical application for polyhydroxyurethanes. In the project that I'm currently working on, we were aiming to solve at least some of these problems. So as I already indicated, polyhydroxyurethanes don't involve the use of toxic isocyanates, can have biomonomers, but are quite hydrophilic. That results in weak mechanical properties and poor processability. And we were thinking and introducing quite simple approach to use aldehydes to form cyclic acetals with these OH groups in polymer backbone that will result in substantial reduction of moisture sensitivity and to increase the mechanical properties of the modified polymers to match them to unmodified PHUs, polyhydroxyurethanes, in dry environment, at all humidities, or even to conventional polyurethanes. to allow this modification, the only prerequisite is that we have two adjacent OH groups in the polymer backbone. And for that, we need like tailored polymers. One of these polymers was previously reported by a group of Ralph Mulhaupt in 2017. They were synthesizing it in solution. So we were starting to work with this polymer, but we adopted a different procedure for synthesis. We were using reactive extrusion. However, we found out that when you just use these two monomers to react in microcompounder, so cyclic reactive extruder, then you don't have a nice polymer at the end, because the cyclic carbonate monomer is not melting at the temperature of the reaction, and it requires higher temperatures to start the reaction and have homogeneous melt upon oligomerizing inside. And also, the resulting polymer has too much OH groups in the polymer backbone that results in excessive hydrogen bonding between polymer chains, and that limits the propagation of the reaction further. So we were trying to adopt another idea from the group of Silva and Kailol, where they used hydrogen bond disruptors. So in this case, we were using like simple solvents that are partially solubilizing the starting monomers, because the melting temperature of bicarbonate analog is like 176 degrees. And at the same time, they disrupt the hydrogen bonding between polymer chains. And judging by the results that we have, the best solvent that we used was N-methylpyrrolidone, NMP. So it gave us the highest molecular weight and the nicest and most homogeneous polymer by appearance. So adopting this solvent, we used 38% in the optimized conditions. We have synthesized two polymers, like one with aliphatic less rigid chain and one with cycloaliphatic more rigid chain that have like adjacent OH groups in the polymer backbone. For the second one, derived from vinyl cyclohexane dicarbonate, we have like different isomers as for the first one, but none of them are favoring further modification that will result in like lower degree of modification for this type of polymer. So then we moved to the modification itself. So first we used a model reaction of butyraldehyde with our PHU-1 polymer to have like a mixture of different isomeric forms inside. And we were optimizing the conditions. We were optimizing the conditions using different parameters like temperature, like time, the ratio between catalyst, which was paratyl sulfonic acid, to polymer, and the ratio of like modification agent butyraldehyde to polymer. So as can be seen from these curves, there's like for time and butyraldehyde modification agent. So the more we have, the higher degree of modification is. For temperature and for the catalyst, there is like optimal condition, a maximum on the curves. And so based on these studies, we selected the optimal conditions for further modification. And to analyze the degree of modification, we used proton NMR. As you can see on the spectrum here on the left at the bottom, there is like distinctive signals of methyl group of butyraldehyde and chain, and then the one of the groups from the polymer chain. So simply dividing the ratios of the integrals of the signals, we were calculating the modification degree. So then we have expanded this method using different aldehydes: aliphatic aldehydes, fluorinated aliphatic aldehydes, and aromatic aldehydes. And as you can see, their modification degrees are a little bit different for these polymers. So the most reactive are aliphatic aldehydes. So as you can see, it's like PHU-1 modified with butyraldehyde, heptaldehyde, or 3-phenylpropanol. So this one is actually an aliphatic aldehyde because the aldehyde group is attached to aliphatic moiety, and benzene ring is like a substituent. Fluorinated aldehyde is the least active, maybe not the least active, it's the most active, but it's so active that it self-polymerizes and does not prefer to self-polymerize instead of modifying our PHU polymer. That's why the modification degree is so low for this aldehyde. Aromatic aldehydes are less reactive, but you can see an increase in the modification degree with the introduction of electron withdrawing groups in the para position of benzene ring. So we were also analyzing the modification degree for this polymer modified with this aldehyde using 3 different NMR methods: proton NMR, fluorine NMR, where we like measured directly how much polymer and how much of like internal standard hexafluorobenzene we added to an NMR tube, and that allowed us to calculate the modification degree, and the more detailed analysis of carbon NMR, and the modification degrees using all these 3 methods matched. Then, to have a nice comparison between the polyhydroxyurethane that we were studying, modified polyhydroxyurethanes, we synthesized a conventional polyurethane that has exactly the same structure except for the absence of OH groups in the polymer chain. And then we were comparing the thermomechanical properties of the studied polymers. So previously in the literature, polyhydroxyurethanes, like people attempted to modify them, but usually it resulted in significant decrease of properties because they used just linear, like acetic anhydride, for example, or silyl chlorides, and that destroyed basically the hydrogen bonding between polymer chains and does not provide any increase in the rigidity. Here we can see that, for example, when we use aromatic aldehydes, we decrease the hydrogen bonding between polymer chains, obviously, because we are like making cyclic moieties of OH groups that we have. But at the same time, we increase rigidity of the polymer chain. That allows us to retain the glass transition temperature for the modified polymers, which was not previously seen in the literature. Moreover, it also allowed us to have the same or even sometimes higher storage modules. That means like the stiffness and rigidity of the polymers that were synthesizing through this modification reaction. And finally, we were studying the properties of our polymers in different humidities, which was the initial goal of this study, to see how this modification can affect the behavior of the polymers at increased humidity. So we have 3 sets of conditions: 45% humidity, it's room basically humidity, 65% humidity, and 85% humidity. And as you can see, the water uptake, which was measured under this controlled environment for polymer samples, decreases when we modify our polymers. So for unmodified one at 85%, it's like 7.5% by weight water uptake after 11 days. And for modified ones, you can see it's decreasing, and the lowest one was observed for this sample at 2.5%. That's obviously higher than the moisture uptake for conventional polyurethane, but much more comparable. And this decrease in moisture uptake can also be seen on like rheological curves. So here we basically measured like in rheology of the polymer samples in a frequency sweep mode. So that allowed us to compare, like, are they the same or different after exposure to humidity in different like humidity environments. So as you can be seen, so for polyurethanes, there is basically no difference in the behavior, in the properties of the polymer after exposure to different humidities for 11 days. On contrary, for polyhydroxyurethane sample, unmodified one, we have huge differences, like almost 2 orders of magnitude. That means that the sample becomes softer, it becomes plasticized, and does not retain its mechanical properties after exposure to high humidity. When we use aliphatic modifying agents like butyraldehyde, we still can see a huge decrease. It's coming from that even if we decrease the moisture uptake, we also decrease the glass transition temperature. And that means that even lower moisture uptake plasticizes the sample so that the glass transition temperature of this plasticized sample is below room temperature. And that's why under measuring conditions, we don't see like retainment of mechanical properties anymore. But like if we see them like modified with aromatic aldehydes, we can see that it allowed us to retain the properties, mechanical properties under the whole range of humidities that we studied. So the decrease is much less than for the unmodified one. And even more, if we take more rigid polymer, so PHU2 derived from cycloaliphatic dicarbonate, we can see also significant decrease in moisture uptake after modification. But moreover, we see almost ideal retainment of the mechanical properties over the whole range of humidities. That comes from combining the modification and a higher, like polymer with higher TG and higher rigidity. So that was basically the method of modification. And then we were thinking about how can we expand it. So we are currently working on several possible expansions. It's like attachment of functional aldehydes to enable CO2 sorption with polymers, to enable synthesis of fluorescent polymers. Also how this modification affects foaming of the polymers. But right now I will be talking about like vitrimers, like recyclable networks based on dioxaborolane chemistry. So a little bit background. So thermosets are cross-linked polymers, as we all know, and they are non-recyclable. However, if we introduce dynamic bonds inside, we can have so-called covalent adaptable networks and vitrimers. Like, what's the main difference? So covalent adaptable networks have only dissociative exchange. That means after reaching certain conditions, all our dynamic bonds break, or most of them break, and we lose the network integrity. And then after cooling or after removing, or for example, of the water or like other agent that allows us to break the bonds, we can have the network back. Vitrimers can have both types of exchanges inside. So, but mainly it's associative exchange. That means that we don't lose integrity of the network during reprocessing, and that defines the retainment of mechanical properties, of the shape of the, like our sample and material throughout the whole range of reprocessing. Polyhydroxyurethanes are vitrimers by definition because this urethane moiety that we have inside the polymer backbone is dynamic, and we also have pendant OH groups that allow us to have associative transcarbamylation. But at the same time, we also have some part, according to the papers that we found in the literature from Professor Torkelson from Northwestern University, that there is also dissociative exchange undergoing. But polyhydroxyurethanes require high temperatures and high pressures to be actually reprocessed. On the other hand, there's another class of vitrimers or covalent adaptable networks is dioxaborolane vitrimers, which like have these dioxaborolane moieties inside, and they can undergo fast dynamic exchange even at the temperatures below zero or like slightly above zero without any additional pressure. And moreover, if we add some moisture, they undergo like work like covalent adaptable networks. The dynamic bonds are dissociated and then can be back reassembled upon removal of this water. So they are moisture sensitive. That's the disadvantage. So, but we have an ideal platform for making vitrimers using this dioxaborolane chemistry because we have these adjacent hydroxyl groups in the polymer backbone. So we were synthesizing two types of networks using two a little bit different procedures. On the left, you can see it is solution synthesis. We dissolved the polymer in NMP and then added the cross-linker phenyl-diboronic chemistry, paraphenyl-diboronic chemistry, and the system immediately cross-links under 5 minutes, and then we wash it with THF to remove the remaining of the solvents, dried to have our network. On the other hand, we tried to use reactive extrusion to make the network without any solvent. However, the conditions that we see here are not enough to extrude the network, so the speed of the exchange of the dynamic bonds is too slow at the selected conditions. So in the future, we plan to optimize it so we can have a nice synthesis in using reactive extrusion without any solvent. As you can see, the cross-linking and the modification significantly increases the glass transition temperatures, yeah, so the degree of cross-linking is quite high. Also, it increases the storage modulus measured by DMA. That means the sample are more rigid. And then when we are talking about vitrimers or covalent adaptable networks, we always study the relaxation, stress relaxation curves, or how the samples relax stress when it's applied to them, and so how they can be recycled and healed, which is the properties of the vitrimers or covalent adaptable networks. So on the left, you can see the stress relaxation curves for the first sample synthesized in solution. But the strange thing that you can see here is that we started from 100 degrees. It was quite fast, 51 seconds. The average relaxation time, 37% remaining deformation, which is like a standard in the literature. But we then drop the temperature below TG, where the material supposed to stay intact and do not relax, but it's still relaxing. And moreover, we can see for the sample synthesized from reactive extrusion method that it still relaxes, but really slow, up to 50 degrees, so almost up to the temperature of the starting polymer. We were thinking a lot what may cause this type of behavior, and we discussed with the colleagues. So far, there are no major conclusions, but one theory is that we can still have some trace moisture inside, not even taking into account that we're drying the polymers really good, but still this trace moisture allows us to have dissociative relaxation of the networks. And finally, so we have networks, but we're thinking that, okay, with the presence of water, we can easily leach out the cross-linking agent. And another idea was to covalently attach it using aldehyde chemistry, and then have the second moiety that will form a dynamic group, dynamic bond, and will allow our networks to relax. So we were synthesizing, first modifying the polymers, then synthesizing the networks, and also studying the relaxation, and it was still relaxing below room temperature. But moreover, we were not able to have a high degree of modification using first attempt. So it was basically more like a chain extension, because two polymer chains were maybe cross-linked once or twice, but not more. So then we a little bit modified the procedure to have high modification degrees, so up to 18%. And you can see that the material in its plasticized state, with a little bit leftover solvent inside and moisture inside, it behaves differently under the stress conditions. Depends on how you stress it. If it's fast, it readily breaks. But if you slowly pull it, it relaxes with the force applied. And then you can see you can stretch it a lot. So it's extremely stretchable. And there are papers in the literature that show it really good. And finally, we were trying to understand why we cannot reach such high modification degrees for our polymers. And we came to the conclusion using NMR analysis that there is a competition between formation of dioxaborolane moieties and cyclic acetyl moieties. So under the conditions of the synthesis, we have this competition, and at the end, we have this kind of polymer with a lot of isomers inside. It's a simplified structure, but we see that some of the polymer chain units are modified with aldehyde function, some of them are modified with dioxaborolane function, and this is the majority, and some of them are left unmodified. So whether we will be able to surpass this limitation, it's not clear so far, but we are currently working on it. And finally, we were thinking about the perspective. Since dioxaborolane moieties are quite moisture sensitive, can we increase their stability? And according to some literature findings, you can do that by making donor bonds between nitrogen and boron that will allow to boost your moisture stability and general stability of the dynamic bonds. And so this is in the plans for the dynamic development of this topic further. At the end, I would like again to thank the organizers for giving me a chance to talk at this conference, and also the funding and all of my colleagues who participated in the project, like Maxim Makarov, who was doing starting to work on this topic as an intern and enlist, and like other colleagues, and Professor Alexander Shaplov, Professor Daniel Schmidt, and Dr. Laura Pouchot. Thank you.